So this is an addendum to the discussion last time about nuclear chemistry. So we weren't able to have a good example on calculations of half-life calculations. So this is an addendum or a follow-up on that. Now, a half-life again is basically the length of time required for a radioactive isotope to become half of its original concentration. So this is a graph of the time in years of your radioactive isotope plutonium-239. Now, plutonium-239, as you can see here, you have your, initially, if you have a concentration, 1.006 grams, after 24,100 years, so that's a half-life, the half-life of your plutonium. The concentration, or rather the mass, is from 1 gram, it becomes 5.5 grams. And then after another 2,400 years, so that means you have 48,200. So this 0.5 grams is halved again. So it doesn't mean that after another 24,100 years, the 0.5 becomes 0. No, it's not. It means that it's 0.5 divided by 2. So you have 0.5 to 0.25. And so on and so forth. So as you can see here, it's not a linear graph. The rate of disintegration or the rate of decay of your radioactive isotope is not a linear graph. It's more of parabolic. It curves towards the x-axis here. So it's more not exactly asymptotic, because there will come a time that it becomes almost negligible. You cannot really detect any more plutonium-239. But it takes a lot of time, as many cycles of half-lives and half-lives to do for it to have a negligible amount of plutonium-239. But anyway, as you can see here, you have a curving graph. So basically, using this calculations of the half-life, you can determine the age of some minerals that contain these types of radioactive isotopes. So let's say, for example, we have americium 243 with a half-life of 70 years. So for a sample containing 10 micrograms, mu is micrograms of the sample. Calculate the mass of the isotope that remains after 22,100 years. So this is the disintegration reaction. Now, we can do it straightforwardly. So how many half-lives do we have in 22,110 years? So if the half-life is 7370, so how many cycles of that? So this is roughly, so divide the 22,110 by 7,370, sorry, it's a bit off. So that's approximately 3. So that means it's reduced 3 times. So you have 10 grams, divide by 1/2, divide by, not divide, times 1/2, times, so divide by 2, divide by 2, divide by 2. So you get 1.25 micrograms. So that's approximately the amount of americium 243 that you have. So these are the table of the different isotopes, radioactive isotopes, and their half-lives. So the most used here is, well, you have carbon 14. This is for organic samples. All organic or living organisms contain radioactive carbon. We accumulate radioactive carbon in our lifetime. When we die, this amount of radioactive carbon decays to nitrogen 14. So we can calculate the approximate time of death, basically, of a certain organic material. And then you have uranium 238. This one was a very large half-life, though. So this one was actually used to calculate the age of the oldest rocks and mineral samples found. So this one was used to calculate the age of the moon, the age of the earth. So let's have another look at radiocarbon dating. So sometimes it's not exactly the concentration of the carbon-14, the isotope carbon-14 that we can detect, but rather, since this is a radioactive material, you can detect the radioactivity using the Geiger counter. So we have, instead of counting how many, determining the amount of the radioactive isotope in terms of its mass, we can just calculate it in terms of its activity. So the activity of a sample of N atoms that is a number of disintegrations over time, over the time observed. So this is actually proportional to the number of the atoms of the radioactive sample that we are looking. So we can have for our equation, instead of getting the fraction of atoms remaining, so instead of getting the mass or the number of atoms, molecules of the atoms, or basically atomic number, no, not atomic number, the number of atoms in terms of n, so we can just since this is proportional, so we can just make it as its activity instead of the actual count of the atoms, since it's just a constant. So remember, since a is equal to a constant times n, and a is a constant times n naught, and a is equal to a constant times n, so the constant will be cancelled out if you divide them. So this is basically a over ao is equal to n over no. So we can just we can use activity instead of number of atoms for determining the rate of radioactive decay. So to calculate the activity, we usually use the Geiger counter, which we already discussed last time. Now, for the Geiger counter, this one measures pulses per minute. So we have units of activity here. Becquerel for that means 1 disintegration per second, and Curie is basically the Curie is the unit for the decay rate of 1 gram of radon. Radon is the radioactive noble gas. So this is equal to 3.7 times 10 raised to the 10 per second, or becquerels. So that's a conversion of Curie to becquerels. So basically, we have becquerel as our SI. Well, as close to SI as we can. So this is actually, it's not first order. The rate of radioactive decay is actually second order. Zero order. Now let's look at our carbon-14 dating. So carbon-14 dating is basically we are getting the number of concentration or the activity of the carbon-14 instead of actually the actual amount. We are looking at the disintegrations, the activity of the carbon-14 in a certain sample. So as the living organisms are living, we have carbon-14, we are intaking a consistent amount of carbon-14 in our bodies. So we have basically a known starting point of carbon-14 for every organic material, plants, animals, even humans. And we have here, as we are living, basically we are accumulating the radioactive carbon-14, and the amount that we are accumulating is around 15.3. The activity, that means the activity of your carbon-14 inside your body is around 15.3 disintegrations per minute per gram of your carbon. That is per gram of all the carbon that you have. So after death, when we die, so we no longer intake food, so that because the source of the carbon-14 is actually the carbon in our food. So that doesn't mean that it's harmful to us. We are actually we have adapted basically to this amount of carbon, or rather radioactive carbon. So we have here the half-life of the carbon-14 is 5.73 times 10 to the third power years. So we have 5,730 years. So the half-life, well, basically when you have around the problem with carbon-14 dating is that when the age of a sample is greater than 50,000 years, the sample has far too little activity, radiocarbon-14, that's left. So the activity is very, very low. So it's very difficult to actually reliably date the samples. So as the sample grow older, the reliability of the results is more or less becomes very unreliable. So anyway, there. Okay, so we have here a problem in this one. Wait lang. Okay, so unfortunately it won't show up in our presentation view, but let's see here. So for example, this is a typical example or calculations we have. So we have carbon-14 dating. So we have an ancient charcoals converted into 4.58 grams of calcium carbonate with a total activity of 3.2 per minute. So you have a sample of an ancient charcoal, and you convert the carbon here into calcium carbonate. and the activity of that sample of calcium carbonate is 3.2 disintegrations per minute. So find the age of the charcoal. Now remember our constant. So we have for carbon 14, it's the half-life is 5,730 years, and the initial activity for any organic for the organic sample of your ancient charcoal or organic material. Actually, it's not necessarily for your organic material per se, is 15.3 per minute per gram of your carbon. Now, if you're going to ask, charcoal is not exactly it's more or less a mineral, but the source of your charcoal is actually organic matter. So it is a petrified organic matter. So anyway, so this is a zero order reaction. So you have the equation for the zero order reaction. So for all calculations of half-lives and for your calculation of your for all the calculations that we are going to use in the decay, radioactive decay, we are using this equation. The zero order reaction, whereas ln of the activity or ln of the amount of matter over the initial activity or initial amount of matter is equal to negative k times t, where k is your proportionality constant and your t is your time elapsed. Now, let's see here. Let's first analyze the problem. So we are looking for the age of the charcoal, that is T. And we have AO. So from our zero order equation, we have AO. So we have AO already. And then we have a total A. That is the total activity of the 4.58 grams of your calcium carbonate. Now, if you look at it closely, our AO is 15.3 per minute per gram of carbon. But this one the activity is 3.2 per minute. That is for the 4.58 grams of calcium carbonate. So we need to convert A to our to the same. It must have the same units as our A sub O. Now, we do not know K, and we are looking for T. So from our zero order equations, we do not know A, we do not know K. So first things first. So let's solve for A first. So solving for the activity in terms of per minute per gram of carbon. So we are already given a total activity, but it's not the exact one that we are looking, because we are looking for the activity in terms of per minute per gram of carbon. So we'll just perform a simple conversion. So for here, you have your 4.58 grams of calcium carbonate, so convert it to moles. And for every 1 mole of calcium carbonate, you have, well, basically we are now here. So for every 1 mole of calcium carbonate, we have 1 carbon. So, and the mass of that carbon is still 0.08. So for 4.58 grams of calcium carbonate, we have 0.550 grams of carbon. And that carbon here is not, all of them are not carbon 14. So some of them are carbon 14, some of them are the stable isotope carbon 12. Now, your activity per minute per gram of carbon, so we will just get the activity. This is measured by Geiger Counter. So we have 3.2 per minute and divided by the grams of carbon that we found. So we have 3.2 per minute divided by 550 grams. So this is equivalent to 5.82 per minute per gram of the carbon. So we now have the same unit as our A sub O. Next, so the next unknown that we do not have is K, the value of K. Now, to find K is actually easier since we already know the half-life of carbon-14. The half-life, again, is the amount of time for a certain sample to become half of its original. So that means the activity, for example, if we have A sub O as 1, the activity of half after 5,730 years, it becomes 0.5. So the ratio is always 1/2 or 0.5. So we can just use this equation. This is for getting the K in the half-life. So we know the half-life, T 1/2 is 5,730. And the concentrations, ln of AO over AO, we do not need the actual values of A over AO. Or rather, we do not need the actual values of A and A sub O for getting the half-life, because again, the definition is the amount of time it needs to get half of the original. And since the equation just demands that we have the ratio of the amount of activity over the original amount of activity. That's basically just a ratio. So the ratio for half-life is always 1/2. So we have 0.5, ln of 0.5 divided by our negative t1/2. That's to find the k, you just divide ln of 0.5 to its negative of the half-life. So this is our k is 1.20968 times 10 to the negative 4 year raised to negative 1. Because remember, how the half-life here is on the time t with the unit of years is in the denominator. So year negative 1. So this is just a proportionality constant. So do not worry that the unit is year raised to negative 1. So now let's put them together. So now from our original equation, ln of a over AO is equal to negative KT, we now know K and we now know A. So let's just put them together. So solving for the time t. So we are looking for the time elapsed for your for the amount of charcoal. Rather, we want to know the age of that ancient charcoal. So we not want to know the time elapsed for the original organic sample with an activity of 15.3 to become 5.82 disintegrations per minute per gram of carbon. So we have your basically just plug in the equation. So we have A from our previous calculation is 5.82. I didn't write the units now here because when we are using ln and log, the units becomes nullified. So we do not really consider the units now when we have lns. Now we have 5.82 over 15.3. So this is equal to the k that we found times the time t. So we now have t is equal to 7,990 years. So the charcoal here has an age of 7,990 years. Or rather, 7,990 years, or rather, the charcoal died, or the organic sample that was the source of the charcoal died 7,990 years ago. So basically, that's it for ratiocarbon dating.